Years ago, we tried to do our search for extraterrestrial life, life on other planets, by setting up giant antennas, big radio telescopes. Their whole job was to look for signals that ET phoned home. But there's been a change. We started to alter how we wanted to look for extraterrestrial life. We've started to figure out that if we actually did come across any radio waves or any means of communications, one, we're not going to know what they're talking about. Two, the things are so slow getting here that by the time they got here, whatever civilization sent them was probably already dead and gone. So we changed what we were doing. Instead of looking for radio waves, we started looking for water. What planets out there in our solar system and in other solar systems could have water? Because what we found here on planet Earth, no water, no life. Water is the most critical thing for there to be life on this planet or any other planet. Look at Mars. Supposedly Mars has some ice, but no flowing water. No water, no life. What is it about water that makes it so important? Well, one of the things is its polarity. Remember last lecture, positive-ish ends, negative-ish ends. That means these positive, negative aspects of the molecules can interact with each other. Opposites attract, North Pole, South Pole on magnets. By attracting towards each other, not forming covalent bonds, but just attracting to each other, they can form hydrogen bonds. The hydrogen bonds are going to be due to the fact that this oxygen here unequally shares an electron with this hydrogen. Remember, spends most of its time over here, and every so often goes there and then back, which means that this oxygen, this one right here, is going to be negative-ish. This hydrogen and that hydrogen, positive-ish. Same with all these water molecules. Positive, negative. Opposites attracting. So, what does this mean in the real world? Well, out there in the real world, all that water in your water bottle, all the water in a lake, an ocean, every one water molecule is hydrogen bonding, interacting with every other molecule. This hydrogen bond, it's not an actual covalent bond, okay? Remember, it's not a covalent. They're not sharing electrons here. What we have is a positive-ish and a negative-ish side of the atoms. They're attracted towards each other. They float by each other, and there's this interaction. Keep in mind, all molecules in this universe are vibrating, are constantly in motion. Your molecules, every molecule that makes up your body, molecules of the desk sitting right next to you. You think is solid. At the molecular level, all these things, atomic level, they're vibrating, they're moving. If it's a solid, they're moving extremely slow, barely recognizable. If it's a liquid, water, they're moving quite fast. So, the state of water, how fast it's moving, how fast the molecules are vibrating, not moving as in a stream or a river, but just vibrating, will determine what state that water is in. Liquid water, like you have in your water bottle that flows out of your faucet. You know, it's in pools and lakes and rivers. These molecules are vibrating, they're moving, constantly in motion. As they're moving, hydrogen bonds are being made, hydrogen bonds are being broken. Because remember, it's not an actual covalent bond, no energy here. They're just opposites attracting. Well, if you add more thermal energy, more heat to what's going on, the molecules will actually start to speed up faster and faster. As the water molecules heat up, the water changes phase. It's no longer liquid, it becomes a gas, steam. The water molecules and steam are vibrating so quickly, the hydrogen bonds don't have enough time to really form that much. All that thermal energy has those water molecules bouncing around very quickly. Now, if you were to take steam and you were to start to cool it, removing the thermal energy, the heat, you'll start to slow down those water molecules. They'll start to form the hydrogen bonds. That water will change phase, go from steam, gas, to liquid. You continue to remove that thermal energy, slowing the molecules down. You go from liquid to solid, what we call ice. Now, if you look at the liquid here in this ocean, this sea, the water molecules may be cold, but they're still in movement, so you have the liquid. Whereas here, the ice, the water molecules have started to line up, starting to form this geometric shapes where all the hydrogen bonds are a set distance apart. The water molecules start to slow down their vibration, their movement. You now have something solid. Now, to change these different phases takes energy. We like to think of energy in the terms of biology as not only the ability to do work, but heat energy. Turns out all liquids have a certain characteristic about them. We call this the heat capacity. How much energy does it take to get them to change from liquid to solid, to go up or down 1 degree Celsius? The heating capacity of water is such that it takes 1 calorie of energy to raise 1 gram of water 1 degree Celsius. You add enough calories of energy. Here, calories is a means of measuring heat energy. You know, we can use Celsius, we can use Fahrenheit, Kelvin, but here, calorie is how much energy is in bonds. So, raise the energy. Continue to raise the energy. What did I say? Happen? You take liquid, raise the energy, keep going and going. You're going to change from a liquid to a gas phase. We call this the heat of vaporization. How much energy does it take to change water from liquid to gas? Turns out water has one of the higher levels of heat vaporization. It takes more energy than many other liquids you can come into contact with. What's interesting is it doesn't matter where this energy is coming from. As long as the energy is present to raise 1 gram of water 1 degree Celsius until it approaches that vaporization point. Well, you ever wonder why you sweat? Turns out the water from your sweat, as it dries, which doesn't do that often here in the South, but other places the sweat does dry, as it goes from liquid to gas, liquid sweat to gaseous vapor. Has to take the energy, needs the energy from somewhere, means it's taking it from your body. So you sweat as a means of cooling. Water is a great, what they call solvent. Its polarity means that anything that is also polar or can interact with other polar molecules will dissolve very easily in water. Water is the solvent. Anything you put in it is the solute. For those of you who like sweet tea, you've seen it. You take an ice cold glass of sweet tea and you pour in a bunch of sugar, sweeten it up. What happens? The sugar goes to the bottom. You have to sit there and stir and stir and agitate. Well, it turns out sugar is a nonpolar compound. Nonpolar does not interact with polar water. Next time you're, in a cafeteria, you're at home eating, instead of grabbing the sugar to put into water or your tea, grab the salt. Salt all but dissolves almost instantly. Why? Na plus, Cl negative. They're ions. Ions interact readily with polar compounds. You look here. You see what is referred to as a hydration shell. The water molecules will orient in such a way that the positive-ish hydrogens are interacting pointed at the chloride. The sodium, positive, is interacting directly with the negative-ish ions. The water will surround the sodium, surround the chloride in all three-dimensional space, forming a shell around it. This doesn't happen with nonpolar things like sugar. Because of this hydrogen bonding, water wants to be drawn to other water molecules. An interesting thing, you take a body of water, whether it's in your water bottle, your cup, your bathtub, a lake, whatever. The water molecules at the surface, well, they don't have anything to interact with above them. So what we find happens is that the water molecules at the surface, here in these, look at this drop of water, the water molecules at the surface of this drop will actually be drawn closer together than water molecules within the drop itself. We call this cohesion. They were drawn closer together, and it gives it what is referred to as surface tension. I mean, look at the picture there on the left. That's a sewing needle that's floating on top of the water. How's it floating on top of the water? It's metal. It should sink. And it would if you went and poked it. Interfered with that surface tension. The water molecules at the surface of the water are so drawn closely together that even the mass of that needle is not enough to break the tension. Another great thing about this, the water molecules, not only at the surface, but within the body of water, since they're interacting with, like I said, a water molecule up here through a series of hydrogen bondings events is also hydrogen bound to water molecule down here at the bottom. They call this adhesion. Where one water molecule goes, they all go. It allows for things like here we see here, this capillary reaction. Come on, you've used a straw, you've sucked up a soda or water. What you're doing is you're using your mouth and your throat muscles to create a vacuum up here in the straw. The vacuum pulls the water at the surface. Because of adhesion, all the other water molecules below also go up the straw. As every little kid knows, you suck up something, your soda, your water into a straw, you cap it with your finger. You can actually hold your soda in the straw. The vacuum pressure is holding the surface tension, the water at the surface due to surface tension, and adhesion holding all the rest. If you're going to do this with some other liquid, such as chloroform. Chloroform has no adhesion, no cohesion going to it. You suck it up, it will move up, you cap it, and it'll immediately run out. No adhesion. This is also what allows trees that are 10, 20, 30 stories tall to pull water from 10 feet below the surface up to 300 feet into the air. They're using adhesion cohesion to pull water up. That's why certain bugs, certain things can seem to float on the surface. You look at the end of the legs for this bug. You see the little dimples. It's spreading its weight out in such a way that it is not messing with the cohesive or adhesive properties of water. That surface tension is maintained, thus it can run across the surface. No other liquid that we know of will allow this to occur.